What if we could manipulate the very essence of light, making it spin around a loop faster than anything we've ever imagined? Let's explore this thought-provoking idea. First, a quick refresher on some relativity basics. Lorentz contraction. It's what happens when an object moves close to the speed of light. It appears squeezed in the direction it's moving. Imagine a spinning disk. As it revs up, its circumference would actually look contracted in the direction of motion. Next is time dilation. As objects speed up towards the speed of light, time literally slows down for them compared to an observer at rest. This means clocks on these speedy objects tick slower. Now envision a hypothetical experiment with me. Imagine a loop, not just any loop, but one made entirely of light. Photons, which are particles of light, race around this loop, continuously rotating. What happens when we speed up this light loop close to light speed? As we crank up its velocity, the circumference of our light loop contracts due to Lorentz contraction. This spinning starts to distort. At some angles, it might seem like the spokes are denser on one side than the other. It's like watching a wheel whiz by so fast that one side seems more packed with spokes than the other. A relativistic effect in action. But here's the kicker. What if we push this spinning light loop even further? Can it go faster than light? At speeds exceeding that of light, the left side of our loop would appear to shift away at superluminal speed. But don't worry, this doesn't break any cosmic speed laws. It's just a fascinating quirk of relativistic physics. As the light loop gains speed, it experiences a phase shift due to the different travel times of light emitted from various parts of the loop. Moreover, the loop's shape appears elongated due to length contraction. So while we can't literally make light travel faster than the universal speed limit, by manipulating it in a rotating loop, we can observe some mind-bending phenomena that challenge our understanding of speed and motion. It's these kinds of experiments that stretch our imagination and deepen our understanding of the universe. Now that we've explored the fascinating behavior of spinning light at relativistic speeds, let's dive into other intriguing effects that occur as we approach the speed of light. One such effect is the Doppler shift. It's the same phenomenon that causes a siren to sound higher in pitch as it approaches you and lower as it moves away. But at relativistic speeds, this effect becomes even more pronounced. Light from objects moving towards us gets blue shifted, appearing more energetic, while light from objects moving away gets red shifted, appearing less energetic. This means that if you were traveling close to the speed of light, the stars ahead would look bluer, and those behind would appear redder. Another mind-bending effect is relativistic mass increase. As an object's speed increases, so does its mass. This isn't just a theoretical concept, it's been observed in particle accelerators. The faster a particle moves, the more energy it takes to continue accelerating it. So, as you near the speed of light, your mass would increase exponentially, making it ever more challenging to gain any additional speed. Then there's aberration of light. At relativistic speeds, the direction from which light appears to come changes. Imagine you're in a spaceship traveling close to the speed of light. Light from all directions would seem to converge towards a point directly ahead of you. This effect compresses your field of view into a narrow tunnel, making the universe look like it's rushing towards you. Lastly, let's not forget about gravitational effects. According to Einstein's theory of general relativity, as your speed increases, your energy increases, and so does the gravitational field you create. This means that at relativistic speeds, you could potentially create noticeable gravitational effects, warping the space around you. These phenomena are not just theoretical musings, they have real implications for our understanding of the universe. They remind us that as we push the boundaries of speed and motion, we also push the boundaries of what we know about space, time, and reality itself. So the next time you ponder the mysteries of the cosmos, remember that the universe is far stranger and more wondrous than we can ever imagine. Now that we've delved into the effects of approaching the speed of light, let's entertain a fascinating hypothetical scenario. What would happen if a light loop collided with another object? When the light loop collides with another object, we enter a realm of intriguing possibilities. Let's explore the consequences of such an event. First, consider the energetic interaction. The collision would transfer energy between the light loop and the other object. Since the light loop is composed of photons, massless particles, it wouldn't experience the typical momentum transfer seen in macroscopic collisions. Instead, the energy exchange would manifest as changes in the loop's rotation or frequency. Next, we have photon scattering. Photons within the light loop might scatter off the colliding object. This scattering could alter the loop's trajectory or cause it to lose energy. Imagine a cosmic billiard game where photons ricochet off the obstacle. Deformation and disruption come into play if the collision's intensity is significant. The light loop, being a hypothetical construct, relies on the perfect circular path of light for its stability. A collision could disrupt this delicate balance, potentially deforming or even breaking apart the loop. In a medium such as air or water, the collision might emit Cherenkov radiation. This eerie blue glow arises when charged particles, like photons, move faster than the local speed of light in the medium. The collision could trigger this mesmerizing effect. On a quantum level, interactions become probabilistic. Quantum effects might see photons absorbing or emitting other particles, such as electrons, during the collision. This quantum uncertainty could introduce randomness into the system. Even though photons have no mass, they carry angular momentum due to their spin. Angular momentum transfer could occur when the light loop collides, transferring this angular momentum to the other object. Imagine a spinning top hitting another top, and you get the idea. If the collision happens near a massive object like a planet or a black hole, gravitational effects would come into play. The trajectory of the light loop could bend, leading to orbital changes or even capture by the massive body. For an observer watching the collision, time dilation and perception effects would be noticeable. The light loop's clock would tick more slowly relative to the observer's clock, making the collision appear to unfold in slow motion. Finally, we must consider the implications of causality and paradoxes. If the collision somehow created a closed time-like curve allowing time travel, we'd face causality paradoxes. Could information from the future affect the past? In our imagination, such a collision could resemble cosmic fireworks, releasing bursts of light and potentially revealing new physics or unexpected phenomena. The universe is a tapestry of infinite possibilities, and even our wildest hypotheses can inspire awe and wonder. As we continue to explore, remember that each idea brings us one step closer to understanding the mysteries of the cosmos. Let's explore some potential challenges and complications that could arise in our hypothetical experiment of rotating light in a loop at relativistic speeds. First, consider the energy requirements. To accelerate the light loop to relativistic speeds, we'd need an immense amount of energy. The energy required to approach the speed of light grows exponentially, making it practically unattainable for macroscopic objects like our light loop. Next, there are material constraints. Constructing a stable light loop is challenging. Light doesn't naturally form closed loops, it travels in straight lines. Creating a circular path for light would involve bending it using exotic materials or gravitational fields. These materials would need to withstand extreme forces and temperatures. Photon interactions also pose a challenge. Photons don't interact with each other directly since they're electrically neutral, but they can scatter off other particles. In our spinning light loop, collisions between photons might disrupt the loop's stability or alter its rotation. Quantum effects become significant at such high energies. Quantum fluctuations could introduce uncertainty into the loop's properties, affecting its rotation and shape. We must also consider relativistic mass increase. As the light loop accelerates, its mass increases due to relativistic effects. This additional mass could strain the loop's structure and alter its dynamics. Cherenkov radiation could occur if the light loop exceeds the local speed of light in a medium like air or water. This energy loss could impact the loop's rotation. Gravitational effects are another factor. Near massive objects like a black hole, gravitational forces could distort the light loop. The loop might spiral inward or experience tidal forces that tear it apart. As we approach the speed of light, we encounter the breakdown of classical physics. Our understanding of rotation, inertia, and geometry becomes inadequate. We'd need a consistent theory of quantum gravity to describe this scenario accurately. There's also the potential violation of causality. If we somehow achieved superluminal rotation faster than light, it could lead to causal paradoxes. Events might occur before their causes, violating our understanding of causality. Lastly, consider the existence of closed time-like curves. If the light loop's rotation creates a closed time-like curve, a path allowing time travel, we'd face logical conundrums. Could we send information back in time?